Hello, everyone. I am back, Mr. Hine. 211, we're starting chapter 2 already. Wow, we just finished chapter 1. Congratulations for getting through chapter 1. It was a lot, covering pre-calc, getting introduced to calculus. But now we're in chapter 2 where it's pretty much just calculus from here on out, and each chapter having its own main objectives. Now, at the start of this chapter, this lesson is going to be on summations and summation notation. That's what you want to take away from this. They talk about in the trapezoidal rule. This honestly is just one approach. It's not necessarily a big deal if you don't get this trapezoidal rule. It's great if you do. It's more important that you just understand how areas of trapezoid works. So trapezoidal rule, it's one approach. I would emphasize that it's more important you know how to find area under a curve using trapezoids. I mean, what will happen, and you'll see this, is that the pattern will emerge naturally. It's not something you have to memorize. All right. So if you don't get it, it's okay. If you understand how to find area using trapezoids, a pattern will emerge, come out naturally. So we'll do this, and this will lead in the summation notation. All right. So say, for example, we had a function x, f of x, and we'll use a table. All right. And we'll say at 0, at 1, at 2, at 3, and at 4. I'm going to make a graph here so we can help visualize this. So x, f of x, and we'll just call it, we'll do x squared plus 2. So f of x equals x squared plus 2. So at 0, you're at 2. At 1, you'd be at 3. At 2, you'd be at 4. And at 3, you'd be at 11. So 3 is somewhere up here at, I'll just mark 11. And at 4, you'd be at 18, which I'll mark somewhere up here as 18. And that's okay. You don't have to have it perfect. It's just a sketch to help us see this. And then we're going to do, let's do 4 trapezoids here. So on this range 0 to 4. So remember that the area of a trapezoid is 1/2 base 1 plus base 2 times the height. All right, the 1/2 is true in all area of trapezoids. Right? And if we make these trapezoids, as a refresher, you have one there. The next one would be here. The next one would be here. And the last one would be here. Right. There's your 4 trapezoids on 0 to 4. Okay. Now, their height is these trapezoids as if you were to turn your head sideways. Right? This right here is the height of every trapezoid because that's the distance between the bases. This is a base 1, base 2, base 1, base 2, base 1, base 2, base 1, base 2. Right. So when we talk about these, to get the height of each trapezoid, you subtract the range and divide by the number of trapezoids, which in this case is 4. So you get 4 over 4, which is 1. So the height of all these trapezoids is 1. So if I was to write area, it'd be area is 1/2. And then base 1 plus base 2 times 1. Now I'm going to write this out for the purposes that I want you to see a pattern because that's how the summation will come to be. So base 1 is f of 0. So that's this distance here, which is the value of the function f at 0, plus f of 1, which is the value of the function at 1. That's the second base. the next trapezoid would be f of 1 plus f of 2 times a height of 1, because it's this base plus this base. The next one would be f of 2, this base, plus f of 3 times the height of 1. And the last one would be f of 3 plus f of 4 times the height of 1. Now, we're adding 4 things here. They look very similar, so some things we can do to simplify this is we can actually pull out the 1/2 and the 1. So we can pull out the 1/2 times 1 in front and just leave f of 0 plus f of 1 plus f of 1 plus f of 2 plus f of 2 plus f of 3 plus f of 3 plus f of 4. And we can undistribute those because each of those have those in common. You could always distribute that back in, but we're trying to simplify it. Now, the trapezoidal rule, what they're trying to show you is that notice that's f of 0 plus f of 1. And that's 1 plus 2, then it's 2 plus 3, then it's 3 plus 4. So these double. All the inside trapezoids double, and the first and the last, which are at your endpoints, only happen once. And that's kind of the trapezoidal rule, is that we could just write here 1/2 f of 0 plus 2 f of 1 plus 2 f of 2 plus 2 f of 3 plus f of 4. And then here, we'll calculate this out the brute force way. And then I will go back and do a summation of this because it might be nice to see. A little bit more advanced, but we'll see how it is. So we would have area is equal to 1/2 f of 0, which is 2. And I'm using my table right here. So 2. Make sure my face isn't in the way in the bottom left. I realized I made that mistake on the last video. Plus 2 times 3, because that's f of 1, plus 2 times 4, plus 2 times 11, plus 18, which would equal 1/2. That's 6 plus 8. So 2 plus 6 is 8. 8 plus 8 is 16. 16 plus 22 is, let me my calculator, I don't want to mess up. Plus 18 at the end. So we get 56 here, and 1/2 of that would give us 28 units squared. And that's the trapezoidal rule of this pattern right here. This technically is the trapezoidal rule. And they generalize it, but at this point, if you're there, that's okay. Now, if we want to do a summation for it, it might look something like this. And this, we'll see. So when we do summations, the summation looks like this, where they do, pull this up a little bit. It's a Greek symbol, capital Greek, I think, for sigma. I'm not sure. And you always have an index down here. It can be any letter you want. So I'll use I equals, and we'll go from 0. And we had 4 trapezoids here, so we'll go 0 to 3. So remember, it's always 1 less if you're starting at 0, because if you start at 0, that's your first one. 0, 1, 2, 3. Notice I have 4 trapezoids still. Going 0, 1, 2, 3, I still have 4 trapezoids. Now, when you do summations, it's all about finding patterns, because what a summation does is it adds things up. That's lack of a better word, but that's what a summation does here. So if I look back at, say, this step right here, notice the 1/2 and 1 I pulled out, so that's 1/2 times 1. And then in the middle, I had f of 0 plus f of 1 plus f1 plus f2. And that, I don't necessarily see a pattern yet, and I could write something like that. But summation is nice because you can take a pattern and write it as an equation, typically a linear equation, because linear equations are things that change constantly. So if I actually come up to the top here, and I'm going to make a preface. This right here, I'll simplify it. This is advanced. Not necessary, but this is a little advanced for writing summation of trapezoidal right away. But if I just look at the first values, f of 0, f of 1, f of 2, f of 3. Notice that it starts at 0 and it has a rate of change of 1. So we could write that as a linear equation of 0 plus 1i. And I'm using I because that's my index there. Right? This right here, 0 plus 1i, that pattern will get me all those numbers when I plug in these indexes. If I plug in 0 first, I'll end up at f of 0. If I plug in 1, which is the next one, because it's going from 0 to 3, 1, well, 0 plus 1 times 1 is 1, then I'll be at f of 1. Right? So that represents the first areas, because there's a pattern there. And I also see a pattern here where I'm starting at 1, and I'm adding by 1s too, so then that's 1 plus 1i. And that right there is, I just wrote a summation of this step of this area. If I wanted to simplify it more, now a little trick with summations is anything that's multiplying, whatever is being added, you can actually pull that out. So I could put the 1/2 in front, and then go I equals 0 to 3. And then if I put this in the function now, the function was, don't forget that f of x was squared plus 2. So if I put that in, it would be 0 plus 1i squared plus 2, because that's, I would put that where the x is, plus 1 plus 1i squared plus 2. And that you could put in a calculator, and it will calculate that for you. Which, if you put in a calculator, you would also get 28 units squared, I believe. Hopefully I did that right. Now let's just get into summations a little bit, because that was advanced for those who are ready for it. But I'm going to start back at just what a summation is. So summation notation. So really quick, summation, say from x equals 0 to 3. So these right here are how many there are. So that means that you're going to plug in 0, 1, 2, and 3. That's what 0 to 3 is saying. And if I have the function, say, x squared, well, that's what you're plugging it into. So then that's going to equal 0 squared. So I plugged in 0, and then once you plug in 0, you used your first index. Then you go to your next index, 1, and then you plug in 1. And then you use your second index. Then you go to your next one, you plug in 2, you use that index, you plug in 3, which is your final index, use that index. And there it is. That's what summation notation is saying. And if you want to write summation notation, so say you had a pattern of 3, 6, 9, 12. Right. No, I'll start back at 0. Why not? So there's 5 things. So you could go from 0 to 4 for the 5 summations. And the pattern here is it's linear, right? Because it's adding by 3. So then I could do 0 plus 3. And I don't always like to use x. X actually isn't common. Usually they use I or j. I'll use j here, plus 3j. And that would be the same notation. So that's why summations are nice, is because you can summarize a whole pattern in one small, it's like a language, small notation. Right? And if you wanted to check this, plug it in. So if you plugged in 0, you'd be at 0. Plus, and then you plug in 1, you'd be at 0 plus 3 times 1, which is 3, which is good. And you plug in 1, you'd be at, or you plug in 2, then you'd be at 6. Plug in 3, 3 times 3 is 9. Plug in 4, which is your final index, you'd be at 12. And that is what we want to add it over there. So there you go. So that's summation notation. This video is an intro. The next video will go a little bit more on how you use these for left and right endpoint.